Hello, let's talk about relations and functions. So you already know about sets, and then let's suppose you want to talk about relations between them also in a formal way. What you can do is you can draw one set on the left, one set on the right, and then literally start connecting the dots. So every element of the left set which is related, you think, to a member of the set on the right will be connected by a line. And anything that's unrelated will not be connected. In that case, all your lines actually form the relation. That's one way, works extremely well with finite sets. You can also take a Cartesian product of these two sets. A Cartesian product always gives this set of tuples, set of pairs, basically, where the first element belongs to one set, the other element belongs to the other set. And then our relation is a subset of that. So it's some set of tuples, not necessarily all of them. A third variant is we can write this graph or an automaton, basically, where every node belongs, every node represents one of the elements of the initial sets, and every edge represents something that is related according to our relation. So this works very well with the case where a relation goes from A to A, but it could also be used in other circumstances. For example, in this case, we don't really know if the green node also officially belongs to the to B, to the output of our relation, and if red one is in A. It could be, but it could also not be. So that makes this representation not complete as the previous one, as this one. But otherwise, it's very nicely visualizing what is going on in the relation, and you will find it quite useful in many circumstances. So when you have a relation, you can again write it just bluntly as a set of tuples. So that's on top. You just say that it is a set. The first element is 1, 2. Then we have 1, 3, 2, 3, and 3, 1. You can also actually do what's in the middle. So on the left you have a set with 3 elements, 1, 2, and 3. On the right you have again a set, the same set with 1, 2, and 3. And then you are connecting the 1 on the left with a 2 on the right, the 1 on the left with a 3 on the right, and so forth. And then third representation is this graph thing where you have nodes for 1, 2, and 3. And you have edges, you have the directed relations that go from 1 to 2, from 1 to 3, and so forth. So these are kind of equivalent. For saying that your element belongs to a relation, you can write an arrow with an R on top, so that you know that you're making one step with this R relation. You could also just write it as a tuple, x, y, and then say that this tuple is an element of that relation. You can also write x, r, y, so the infix relation, infix notation for a relation works nicely with binary relations, but not really beyond that. So then you can switch to a prefix notation, and you can also put brackets. So in with functions, people usually put brackets around them. What things can we do with relations? Basically everything that we could do with sets, so union, intersection, difference, these kind of things. But we can also do inverse. So an inverse is a relation which is filled with tuples that are basically inverted with respect to the original relation. And then we have a composition, which is two relations. Let's say R goes from A to B, so it is a subset of a Cartesian product of A and B. And then S goes from B to C. And then it consists of tuples xz, for which there is some kind of middle point in B, so that from x to y you can get with R, and from y to z you can get with S. and then you first apply R and then S, and you write it as S applied to, or S composed with R. And obviously, if you compose R or any kind of relation with its inverse, then you will get an identity function. So what is a function? So if this is a relation, what do we need to make it a function? One thing we need is a direction. So a relation, yeah, we talk about things on the left, things on the right, and this kind of things, but inverse of a relation always exists. Reverse of a function does not always exist, or does not always satisfy all these laws that we want it to satisfy. So we want to give it a direction. And then we do not want to have this situation of non-determinism, when we have one input that could possibly result in two different outputs. So this is sometimes called right uniqueness, and then it's also called a functional relation. So then this relation could be a function even if we do not have the arrows. Another thing is then you have an injective relation. An injective relation is does the same but for the other way. So it means that you should not have collisions where you map two distinct elements of your set A to the same element in a set B. So formally specified as shown below, which basically says that if you have two elements of A and there is an element of Z that both are mapped to, then X equals Y. This relation is usually called injective, so it could be injective relation or injective function. We also have surjective relation or function, which basically guarantees that we do not have leftovers in our target set. So for every element in the target set, we have some part of our relation that goes there. And then we have this bijective relations and functions that are basically injective and surjective at the same time. So to summarize, we have relations and the whole calculus based on them. It is based on sets, and it mostly uses stuff from set theory. We can have three representations. We can just draw them as we like and then connect the dots. We can draw them as automata, as graphs, as directed graphs. We can also treat them formally as a set of tuples. And those relations can be injective, surjective, and bijective. Thank you. That's it.